Hello and welcome to the web series ZeroPM Pieces. In the ZeroPM Pieces, the researchers in the project will tell you about one piece of the ZeroPM puzzle that they're working on. So without further ado, here comes a ZeroPM piece.
Hello everyone, my name is Abishek and I am a PhD student at the Fraunhofer Institute for Toxicology and Experimental Medicine, and I'd like to speak about the PBK modeling using IVIVE to predict the toxicokinetic profiles of triazoles, and it's a part of the ZeroPM pieces, the piece number 22. I belong to the work package 6. The work package 6 main objective is to do the risk assessment and the hazard assessment for the persistent and mobile substances. So here we belong to three sub tasks or three sub work packages. Task 6.1, which speaks about the environmental fate and exposure model, the external exposure, I would say. The task 6.2, which is the EVV based PPK model, which translates the external exposure to the internal concentration, internal human concentration using the PBK model, and the task 6.3, which is a toolbox for the hazard assessment using the in vitro test assays and methods. So let me elaborate the task 6.2, which is the kinetic assessment for the persistent and mobile substances. So here we see a flow chart at the start, which is a hazard identification, which has been carried out by the task 6.3 using the toolbox, and the hazard characterization, how much hazard is prevalent within the humans, has been estimated using hazard characterization using the PBK model, which is exactly what task 6.2 does. And then we see a workflow down, which says that there is a generic eVivo based PBK model, an in vitro to in vivo extrapolation based PBK model for a data rich compound, and then we model the compound using the compound specific parameters like the ADME parameters, I would say, the fraction unbound, the intrinsic hepatic clearance, the absorption using the PAP assay, and the fourth one is blood plasma ratio. And then characterize uncertainty of the model, and then improve it if it's necessary, and then extrapolate to the various other substances in the family, in the group, using read across approach. So this is the overall schema of 6.2. And then now I'd like to elaborate on the compound selection. So we have three groups of compounds: triazines, triazoles, and PFAS. So triazines are compounds with azine ring, and then here we see that there are data-rich compounds like with a lot of information and studies which has been into it, which are cytomycin, melamine, atrazine, etc. They are like really well studied. And then there is data poor compounds, which there is not much studies which have gone into it, like cyanuric acid, amylin, diethylatrazine, and so on, for in the case of triazine. And our emphasis today is on triazole, which means to say that tridimenol, tebuconazole, they are like really well studied compounds. The triazole acetic acid and other triazoles are not really well studied, and there is not much information available in the literature for these compounds. So that's the idea behind the compound selection. And now I'd like to speak about the PBK model and its application in the key viewer process. So we see that there is an in vitro test assay at the left corner here, and then we get the in vitro test dosage response, and then we correct this response using a vivid model. I'll come to in a moment what's the vivid model and what does this do. And then we have a PBK model, which is a set of mathematical equations which gives a concentration, the plasma concentration or a tissue level concentration within a human or a rat. And then we perform a reverse dosimetry, also a forward dosimetry, like from the concentration from the external environment, which has been again translated to the human using the PBK model. So it is a two-way communication using a PBK model to with in vitro test assays from battery, and also from the external concentration from various databases and sources. So I'd like to speak about what vivid model is. It is a pre-developed model at the Satara by Fisher C et al. In 2018. So at ITEM, we use this paper as a source and then redeveloped or reutilized this model with its equations, and then it is a model which says a free medium available concentration within an in vitro test assay. For example, here we see a cell system, and there's cells within it, and then there's media. And so, for example, if a chemical is dropped, we are sure that it can partition within the cells, or can just stay in the medium, can do partition to the air, and also get absorbed by the surface, that's the plastic um, in the cell system. So all these are taken into consideration along with ionization of the compounds, which is very important for the persistent and mobile compounds. And then we finally come to conclusion like how much is left available just in the medium. So this is a very comprehensive model when we go through the literature, which takes more or less everything into account, the protein binding, the plastic binding, and so on in the system. So what happens here? So here's a vivid model, which is free medium concentration. The comparison, for example, the blue lines represents the nominal concentration which has been administered within the system, and the green bars represents the concentration which has been measured using the mass spec analysis, and then the yellow lines depicts the prediction from the vivid model. And we see that for the vivid model, more or less like the concentration matches with the medium measured concentration. I mean to say that the measured concentration and the predicted concentration are really close by and within the factor of 2, which is a very good observation, except for the fact that for PFOS and PFOA, the model kind of underpredicts because of higher plastic binding and higher protein binding and so on. So PFOS and PFOA has proven otherwise with the test assays, but more or less all the triazines and triazoles, they are good enough. They are fine for the model prediction versus the measured concentration from the mass spec analysis. So and I go in deeper what's happening within the cells, the intracellular concentration. Apart from these 4 compounds, atrazine, amylite, tebuconazole, and triadimenol, the other compounds are within the factor of 2. They are very good. The measured concentration versus the predicted concentration, not really far apart, I would say. So these 4 compounds are the one to be taken into account. And there could be multiple factors why it's not in the same range, and then we see a huge variation between the measured and the predicted value. So what are the uncertainties? So there could be multiple uncertainties, like the model works good for triazines and triazoles, but not so good for PFAS. And then also within the cells, there is a discrepancy, as we discussed. Maybe I could do a sensitivity analysis with different assumptions and see what could be the difference. There could be also a possibility that the measure value showed fluctuations, and then yeah, maybe better technique or better method could be used for measuring. So there could be a lot of uncertainties in my opinion, and then I do sensitivity analysis to counter this. And here we have an in vitro parameterized bottom-up PBK model. So bottom-up PBK model is a set of mathematical equations which remains more or less constant, and then we use in vitro tested test battery assays, as I mentioned earlier, the absorption by the CACO2 assay, the barrier model, to see the KIT or the gastrointestinal tract absorption, and then we go through the in vitro intrinsic hepatic clearance assays to see if there is any metabolism happening within the liver cells and this is also measured from the in vitro ADME test assays. And also the fraction unbound, which means to say that how much percentage of the substance is is freely found in the blood and not bound to the blood plasma proteins, which is also an important parameter for the PBK modeling and its assessment. So yeah, and here I would like to show a specific example like tebuconazole, which is a rat specific oral route PBK model. Why do we do it with rat? So for example, all of these chemicals are we do not have any plasma concentration curve for the humans. So we start with the rat as a proof of concept and then further extrapolate to the humans. So that's the basic idea behind it. So it's a rat-based PBK model, bottom-up PBK model for a human for a rat, male rat of 350 grams. So that's the assumption behind it. And then we use the apparent permeability, which has been measured in-house by Tanya Hansen. And then we do have the intrinsic hepatic clearance from varied sources, like from the Comtox measured and also from a paper using microsomes. And further, the fraction unbound, which is 7%, which is also from Comtox. And then we have varied values, the maximum solubility, the log P, the ionization status, everything goes within the PBK model as inputs. So what do we observe here? So we use various clearances, as I mentioned in the previous slide, and then this is a male rat of 350 grams. And then we see that there are a lot of blue dots, which represents the in vivo test values, in vivo measured values, I would say, from the FSAR report. And then there are like various lines, like the red line represents the microsomes clearances from rat, and then the orange and the blue lines represents the clearances from the intrinsic hepatic clearance from the primary human hepatocytes. And we see that for the further extrapolation, the PHH suits better because it's within the factor of 2. The maximum concentration attained, the time in which the concentration is attained, and the area under the curve, everything is within the factor of 2, and it's a good prediction, I would say, for the PBK model. And also the clearance is taken from the intrinsic hepatic clearance along with the glomerular filtration rate, which is an important role in determining the clearance. And care has to be taken that the in vivo data accounts for overall radioactivity of tebuconazole, also, which could also include its metabolites. So it is it's an estimation based on the overall radioactivity and not just the parent compound. So what do we observe in this slide? Here we have a tebuconazole for a human extrapolation. So there is LOEL, the lowest observed effect level for the human, which has been allometrically calculated from rat. So for the rat, the value is around 5.3, and then we divide it over 4 for the human extrapolation, and it's 1.3 to 5 milligram per kilogram for human. And then we see that it's a single exposure, like human male of 70 kilogram has been exposed to once, and then this will be further extrapolated for a continuous exposure for 5 days or more to see a steady state plasma concentration for the Cmax, the concentration maximum, and so on. So that's the upcoming step to do here. And here we see that the red block is the upcoming steps which I have to do, and then the ones with the tick at the left represents the steps which have been already carried out, like in vitro biokinetic assay response, which has been corrected by the Weber model, which is done. And then we have to do the further simulate an external exposure scenario from varied database sources for the drinking water and groundwater concentrations, and then compare the plasma concentration from this external exposure to the in vitro test assays. So these are the upcoming steps in my workflow. And then further steps in PBK model. So run a rat-based PBK model and then perform the uncertainty and sensitivity as per the OECD guidelines. Yes. And then extrapolate to the human for all the triazoles and followed by triazines and then followed by PFAS. and then read across approach. So parameterize the data-rich compounds with available data and the data-poor compounds with read across approach, and then perform a reverse dosimetry to estimate the internal concentration within the human and to compare it with the in vitro test assays. So these are my points, and thank you so much for your attention. And it's questions time.
ZeroPM, Zero Pollution of Persistent and Mobile Substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under Grant Agreement number 101036756.